Okay, so this is question 13 on page 480. So this is using oxidation numbers to determine whether or not a reaction is a redox reaction. So the first compound we have is hydrogen peroxide H2O2. And from the set of rules, hydrogen is always a +1 unless it's with a metal, so metal hydride. And oxygen is not a metal, so that means that this is not an exception to that rule. Hydrogen is a +1. Oxygen in the rules is a -2, and if we look at the exceptions, one of the exceptions is in H2O2 or hydrogen peroxide, where oxygen is actually a -1. So one of the rules is that the overall oxidation numbers have to add up to the charge of the compound or atom or ion. So here, H2O2 is neutral. So I have two hydrogens that are each +1. So hydrogen in total is a +2. And I have two oxygens, which are each -1. So -2 total for oxygens. +2 minus 2 is equal to 0. So that gives us our overall neutral charge. For iron 2 hydroxide, there's a few different rules we can look at here. So hydroxide is a polyatomic ion, which has a charge of -1. And so the oxidation numbers for oxygen and hydrogen have to add up to -1. So if we look at our rules for oxygen, oxygen is a -2 and hydrogen is a +1. -2 + 1 is equal to -1. So those are our numbers for oxygen and hydrogen. Now we don't have to put our oxidation numbers for oxygen and hydrogen separately above when we're accounting for the total number of atoms of each element. So here we have two hydroxides. We know that as a unit, hydroxide is a -1. And so our oxidation numbers for each atom, for oxygen and hydrogen, we have based on that. But now we can just say that hydroxide as a unit is -1. And I have two of them. So I have -1 and -1, which gives me an overall of, not -1, -2 for hydroxide. So at this point, if you prefer to do each element separately, you can. So two hydroxides means two oxygens. So I have -2 and -2, which would give me -4. And hydrogen, I have two of +1 and +1, which gives me +2. So when I'm figuring out iron, I know that my total, so I have one iron, and I have my two oxygens at -2 and my two hydrogens at +1. And that needs to equal 0 because overall iron 2 hydroxide is neutral. So I have some number -4 + 2 equals 0. So x is equal to 4 - 2 or 2, and that's a +2. So the other thing that I could just do is, because I have hydroxide as a unit, I could say 2 times -1 for hydroxide. So x plus that equals 0. So x - 2 equals 0, x equals 2. So it's just less work if you use any polyatomic ions as their whole. So here I know that iron overall needs to have a +2 because I only have one iron that is not split between multiple atoms. So iron is a +2 here. And then on the other side, I have iron 3 hydroxide. So hydroxide still needs to have -1 as its total. So we've already taken a look at that. So that means oxygen is a -2, hydrogen is a +1. So that part stays. The part that becomes different is here, and I'm just going to get rid of the minus charge there. Here we have 3 units of hydroxide. So once again, I could just say overall hydroxide is a -1. And so as a unit, if I have 3 of those units, then overall my hydroxides have oxidation number of -3. But then I could also do it separately. So I have 3 oxygens at -2 each, which is -6, and 3 hydrogens at +1 each, which is +3. So this is your option, whether you want to go through this process and doing it for each atom, or whether you want to use your polyatomics together here. So this means then that my overall charge for hydroxide here is a -3. To counteract that, to end up with a neutral charge, I need a +3 for iron. And once again, I only have 1 atom of iron here. And so that's going to have a +3 as its oxidation number. I'm just going to get rid of all this rough work. And then we'll talk about our comparisons. So, and I'll just switch to a different color here. So I have hydrogen in the reactants has +1 over here, and in the reactants, or sorry, in the products, it is also a +1. So hydrogen's oxidation number did not change at all in this reaction. Oxygen has a -1 here, a +1 here, sorry, a -2 here, and a -2 here. So we have some that are a -1, some that are a -2. And in the product side, all oxygens are a -2. So what this means is any of the oxygens that came from iron 2 oxide remain the same, but any of the oxygens that came from hydrogen peroxide have actually changed their oxidation numbers in the products. So that right there tells us that we have a redox reaction because we have had a shifting in where the electrons are found, how close they are to each atom. We can also look at iron though, which is a +2 in the reactants and a +3 in the product. So that also shows a change in the oxidation numbers. So this reaction is a redox reaction because there was a change in oxidation numbers. So you only have to have a change showing up for at least one thing. Now it's typically going to be in more than one because a redox reaction has a gain and a loss. So usually one thing is gaining and another thing is losing. But because you can have reactions where you have an element showing up in different compounds, that one element could end up accounting for both changes. So sometimes you could have sulfur that has a +4 in the reactants, and then you have 2 different options in the products where sulfur shows up. Once is a +2 and once is a +6. So to go from +4 to +2 and +6, some would have lost and some would have gained electrons. So you can have all of your change happening within one element, but you would see both the gain and the loss within there. So here we saw not quite that. We saw some change with oxygen and then some staying the same. So here we needed the other difference to happen from somewhere else. But this is a redox reaction because we do have, for different elements, they don't have the same oxidation number all the way throughout. So as long as there's a change, that is a redox reaction. Oops.